Inverse Functions and Logarithms Part 2. Now it's time to look at logarithms and see if we can go ahead and just quickly review the laws of logs and discuss ways of looking at limits when you have functions that involve logarithms. So the first thing is just a very fast review. If we have a positive base not equal to 1 and we know x is greater than 0, then the function f of x equals a to the x is a one-to-one function and it's differentiable. Because it's differentiable, we know that f has an inverse function, and the logarithmic function with base a is that inverse function. So the property does hold so that if you interchange the domain and range of one function, you get the inverse function. That's what you're seeing here. That's what you're seeing here. You're seeing that if y equals log base a of x, what I'm going to do is interchange the domain and range. So my input was the old output, my output was the old input. So if f of x equals a to the x, this is only true if the inverse of x is equal to log base a of x. And so we know that we have properties of functions composed of their inverse. You evaluate the log base a of x at a of x, and you end up with x. And this is for all x in the real numbers. Let's fill in that box. All x in the real numbers. And if I compose a function with its inverse in the other direction, a raised to log base a of x, again, that's equal to x. But now we have to make sure x is simply positive because my domain for logarithms are just positive numbers. You have to be aware of that change of domain. Log base e of x we refer to as a natural log of x. This is our natural logarithm. And so that will correspond to exponential functions with base e. Again, continuing with the review, we know that if I write down y equals log base a of x, a is greater than 1, we have a typical graph in mind. And that typical graph in mind is very different than the graph you get if a is between 0 and 1. Notice for both graphs, what is similar is that the domain are positive numbers, while the range is all real numbers. And notice what is similar is that log base a of 1 is 0 and log base a of a is 1. That's true on both graphs. But what differs is the behavior of the limits. The limit as x approaches 0 from the right, well, it looks like those outputs are getting smaller negative-wise. And so the limit of log base a of x is negative infinity so long as your base is greater than 1. As x approaches infinity, what would the limit of this function be?
Going towards infinity.
Very good. Now contrast that to what happens if your base is smaller than 1 but larger than 0. If I look at the limit as x approaches 0 from the right, what would that limit be, would you assume?
That'd be infinity.
And if I looked at the limit as x approaches infinity,
Negative.
Negative infinity would be the limit. Very good. And that's what we're seeing here. So with this said, all we're going to do is we're going to remind ourselves that because these are inverse functions, we have symmetry about the y equals x. And if you're dealing with e to the x, well, the natural log of e to the x is equal to x for all x in what? In the
all real numbers.
Real numbers. And e to the natural log of x is x, but there again, you're putting in values of x that are only positive. All right, continuing with the review, because you have a base e, which is approximately 2.71828, that's greater than 1, we know the limit as x approaches 0 from the right is going to be negative infinity. What would the limit be as you approach infinity for the logarithm function, natural logarithm function?
Would be infinity.
Very good. All right, let's look at laws of logarithms. We've seen this before. If x and y are both positive, when you go ahead and add two logarithms, you can multiply their arguments. When you subtract two logarithms, you can divide their arguments.
Right.
And when you go ahead and multiply a number to a logarithm, you can absorb that number as the exponent on that particular argument. So for example, if I wanted to simplify log base 2 of 80 minus log base 2 of 5, I notice a couple of things. But the first is that I can go ahead and say, since I'm subtracting, then I can notice, because I have the same base, I could do what to the actual arguments? I would
You can divide them.
Divide them. And so this gives us log base 2 of 16. But again, if you're looking at a logarithm function, to remember If I had log base 2 of 8, this means that 2 to some exponent is equal to 8. 2 to some exponent is equal to 8. And so that exponent would be what? It would be
3.
3. So this says 2 to what exponent is 16? Well, that would be
4.
4. And so we can go ahead and say it's 4.
Yeah.
We can spell it out with our rules of logarithms if we want, just as easy. For a change of base, if a is greater than 0 but not equal to 0, we know that log base a of x is equal to a natural log of x over the natural log of a. It enables us to find the value of any particular logarithm other than the two bases on your calculator, which are 10 and e. So for example, if I want to evaluate log base 3 of 7, correct to 5 decimal places, I would go ahead and write my new quotient as the natural log of 7 over the natural log of 3. What is the natural log of 7?
That is 1 point, how many decimal places? 5. So
5.
1.94591.
What is the natural log of 3?
That is 1.09861.
So if I go ahead and divide those two numbers, it's approximately 1.77124. Let's just check it real quick. If we're saying log base 3 of 7 is approximately 1.77124, then this means that 3 to that value should equal 7. So take 3 and raise it to the 1.77124, and out the 5 places, read me the result.
It's 6.99997.
And we have a quick way of checking our answer. All right, let's look at an example. We're going to expand the natural log of x cubed y over the square root of z. And all we're going to do is say everywhere we're dividing in the argument, we will subtract natural logarithms.
Yeah.
Which means everywhere we're multiplying in the argument, we'll do what with the natural logarithm?
You can add them.
Add them. Okay. Now, what else can we do? What can we do with those exponents on the arguments?
You can bring those to the front.
Bring those to the front and multiply the natural log by them.
Right.
And all of a sudden, we have our result. Let's try it again. Let's see if we can go ahead and expand. So in one sentence, tell me what the expansion would look like if I say everywhere I multiply in a argument, I'll do what with the actual logarithms?
You add.
And everywhere I divide within the argument, I'll do what with the logarithms?
You'll subtract.
So what would my next line read as?
So it'll be the natural log of x to the 17th plus the natural log of the square root of x minus 1.
And what exponent would represent a square root?
1/2.
Good. And what would be the third term?
It'd be minus the natural log of 3x minus 13.
Very good. We could look at one more step. What am I thinking about for that next step?
Is it bringing the exponents forward?
It is bringing the exponents out front. So what would we end up having as a result?
You'd end up with 17 times the natural log of x
Very good.
plus 1/2 times the natural log of x minus 1
Very good.
minus the natural log of 3x minus 13.
Excellent job. So we have expanded into as many logarithms as we can. We have 17 logarithms here, half a logarithm there, and so on.
Yeah.
All right. Now let's use the properties that we have to see if we can solve for x. Now x is kind of trapped up in the exponent, and I want to remove it. So when I write down e to the 1 minus 4x and set it equal to 8, my first goal is to remove x from the exponent. And how do I do that? What do I do on both sides of the equation?
Take the natural log of either side.
Okay, and I'm doing this for a specific purpose so that in the next step, I'm going to end up doing what?
You'll pull the exponents to the front.
Very good. And now x is not trapped in an exponent anymore.
Right.
So I have 1 minus 4x, quantity, times the natural log of e is equal to the natural log of 8. Refresh my memory. What is the natural log of e?
That's 1.
That's 1. So I'm going to go ahead and say this leaves 1 minus 4x is equal to the natural log of 8. Now I just need to isolate x.
Yes.
I'm seeing two steps. Are you seeing two steps?
Yeah.
What are the two steps?
Subtract 1 and divide by -4.
All right, so I'm going to subtract 1. This leaves negative 4x is natural log of 8 minus 1. And the last step you said was to what?
Divide by -4.
Divide by -4. So I can write x is equal to natural log of 8 minus 1 over -4. That would work. Or I can bring the negative out front if I wanted to. And then I'd have the natural log of 8 minus 1 over 4. And that negative out front would reverse the terms up in the numerator. Either variation is fair game. Is this checkable?
Yes.
Yes. I can enter this into the calculator. And when I do that, I can go ahead and write in my original function. And whatever number I get, I can put it in the table. When I do that, my output here should be an 8.
Got it.
Does that make sense? I'll go ahead and evaluate this as the x-coordinate. Substitute it into the table feature, and the output would be 8.
All right, yeah.
Let's do one more solving problem. Solve for x. Now x is not trapped in an exponent. No, it's trapped in a?
In a natural log.
In a natural log. So I got to remove it somehow. So the first step is to isolate that natural log. What does that mean? What will be my first step?
Will you... I'm not sure.
All right. I want the natural log by itself on one side of the equation, everything else on the other.
Okay. So you would start by subtracting the 13.
Okay. Let me go ahead and catch up with you. And then I really want natural logarithm equal to a number.
So divide the -1.
Okay, divide by -1. So this leaves the natural log of what on the left? Natural log of?
3 minus x.
And what's left on the right?
13.
13. Now, why did I want to isolate the natural log? Because I need to undo it. How do I undo it?
Do you put it in the exponent of e?
Okay, so what we're going to do is we're going to now switch forms. Very good. We're going to switch to exponential form. All right. So again, a logarithm is read so that you take the base, it's read circular, to the exponent is equal to that argument. 2 cubed is 8.
Yes.
So here, what is my base for a natural log?
E.
So I'm seeing base e. So it's e to the what? E to the?
E to the 13th
is equal to?
3 minus x.
And now at this point, I have a comfort level. I'm just going to solve for x. My steps are to do what?
Right, so you'd subtract 3.
All right, so it leaves e to the 13th what? Minus?
Minus 3.
And my very last step, since it's now equal to a negative x, would be to?
Divide the -1.
Divide by -1. So I got negative e to the 13th plus 3. Or more commonly, 3 minus e to the 13th.
Right.
All right. Well, now what I want to do is look at a couple of limits. Now, the way limits work with natural logarithms is when I approach 0, the way limits work with natural logarithms is when I approach 0, then what I want to do is find out how is the argument behaving. Once I know that, I can then say how would the natural log of the argument behave. It's 2 different steps. I'm going to let x approach 0, and then the argument I'm going to call t. How is that behaving? Well, if x approaches 0, then the sine of x approaches 0, because I have this visual of the sine function, don't I?
Yeah.
If you're approaching 0 from either side, the sine is, the outputs are getting close to 0.
Yeah.
And since sine is getting close to 0, when I square sine, I'm getting close to 0, but the numbers are all positive. And that's what you're seeing in front of you.
Okay.
Now you say, what happens when the natural log of sine squared x is looked at? So you do a change of variable. You say that argument is now t. And let's look at the natural log of t. Well, as t approaches 0 from the right, what does the natural log of t do? Remember the graph the natural log function.
Right.
Here's t. Here's ln of t. As you approach 0 from the right, what's the graph doing?
It's going to negative infinity.
Going to negative infinity. Very good. Let's see if you can take a look at this next problem. We're going to find the limit. And what I see is not one, but what? But
two natural
two
logs.
natural logarithms. And they're being what? They're being subtracted. So when I subtract two natural logarithms, I can find one natural logarithm by doing what?
You divide the two.
I would divide the two arguments I see.
Yeah.
So now I have the limit as x approaches infinity of the natural log of what?
1 plus 9x over 5 plus 2x.
Very good. Now, x is approaching what number?
X is approaching infinity.
Infinity. So I have 1 plus 9x, that's shooting to infinity.
Yeah.
I got 5 plus 2x, that's shooting to
Infinity.
too much for me to think about. So I'm going to divide everything through by what? I'll divide everything through by
The largest x.
largest x in the denominator.
Yes.
So let's do that. We have the limit as x approaches infinity, and if I divide the numerator and denominator of the argument by x, I now have the natural log of what?
Of 1 over x
Good.
plus 9.
Okay, and what's in the denominator?
That'll be 5 over x plus 2.
Very good. And although you don't need to show it, you're actually doing 1 over x plus 9x over x. That's how you got to where you arrived at, right?
Yeah.
You did 5 over x plus 2x over x. That's how you got to where you arrived at, right?
Right, yeah.
All right. Now, as x is approaching infinity, what is 1 over x doing?
It's approaching 0.
And what is 5 over x doing?
Approaching 0.
I can see my answer. What is my answer here?
So it's 9 over 2.
Very good. It's the
The natural log of 9 over 2.
natural log of 9 over 2, or the natural log of 4.5. Excellent. Let's do one more. This one is a little bit irritating, but you won't find it so irritating, will you?
I will not.
No, you will not, no. Because what you're doing is you're saying, as x approaches 0 from the right,
Right.
what is the sign of x approaching?
It's approaching 0.
Very good. And it's approaching it from the right because if I graph the sine function, as I move to the right, aren't all those outputs what all those outputs are?
Going towards 0.
Going towards 0, and they're all what? They're all
Decreasing.
decreasing, but they're all
Going towards 0.
from the
right.
From the right.
Oh,
Okay. So that means that now I'll rewrite my limit as the limit as t approaches 0 from the
right.
From the right. And I have the natural log of what I used to call sine of x, and now I call
The natural log of t.
we have the natural log of t. So this question should sound a little bit familiar. Imagine the natural log graph. Okay, here's t. Here's ln of t. As you approach 0 from the right, what is that limit going to be for the natural log of t?
Negative infinity.
Negative infinity. Excellent job. Thank you.